simple harmonic motion can be used to approximate the motion of a simple pendulum. In this video, I'm going to explain the maths behind that and why we can do such a thing. And then I'm going to go through one worked example. Okay, so a simple pendulum is quite simply an object that is fixed to one point, usually on a horizontal ceiling. And then it has perhaps a string or maybe a rigid rod, an inextensible string as well, or a rigid rod, which then has a mass on the end. For this modelling, we will assume the mass of the string or rod is light. So the only mass that comes into play is the mass of the bob, the pendulum bob. And then what's going to happen is as you pull this mass to the right and let go, it's going to swing back and forth, kind of like a grandfather clock. Just one of those simple pendulums that just swings back and forth. Because this is a fixed length, then the path that this is going to follow is going to be part of an arc of a circle. Okay, it's going to be an arc, and that's important when we come to find the distance it's going to travel in time. Okay, so let's look at the forces acting on my mass. I've taken the anti-clockwise direction to be positive, which is generally true for maths. So as the pendulum swings to the right, theta is positive, and then if the mass swings then to the left, then theta will be negative. So my diagram shows a positive value of theta. Okay, so here's my mass, and let's consider all the forces that are acting on it. At any given time, you've got its weight, which is acting vertically downwards. And then you also have the tension in the string or the rod or whatever this is, and that's going to be acting up there. Which I don't actually care what that is, because whenever wherever this mass is in time, we will always be moving perpendicularly to this tension force, because this tension force is a radius, and it's going to be moving tangentially along the arc of the circle. So if theta is increasing that way, then that means my acceleration is positive that way. And I'm also going to pop in this angle here, which will be the same as theta. Okay, so theta is going to vary with time. X double dot is to the right, that's my positive direction, and then mg is acting vertically downwards. So if I now resolve the forces on this mass, then I'll end up with minus mg times the sine of theta, and that is going to be equal to the mass times the acceleration. Okay. Now, what we really want is a differential equation which contains one dependent variable. At the moment, I've got theta and x, which both vary with time. But I can relate theta and x. If you go back to this diagram here, x is going to be the distance it's travelled along the arc of a circle. And then theta is measured in radians, because we're going to be doing calculus on some trigonometry. So therefore, this arc length, which I'm going to call x, must be equal to the length of the radius times theta. It's just from regular A-level maths. L is a constant, okay, that's just the radius of my circle. X is the distance travelled around the arc. Theta is the angle subtended at the pivot, and I can therefore differentiate this twice to give me x double dot is equal to L theta double dot, okay, because L is a constant. So if I use this definition and plug it into here, and then cancel the masses and do some rearrangements, I can end up with the differential equation x double dot plus g on L, sorry, not x double dot, theta double dot plus g on L sine of theta is equal to 0. Okay, so I've used L theta double dot in for x double dot, which means that's why there's an L here now, so we divide the whole thing by L. The masses have cancelled, so the mass doesn't even come into it, and we can see this is now a differential equation, which will govern the motion of the pendulum. However, this is not the simple harmonic motion equation, because I have a sine of my dependent variable, not just my dependent variable. Okay. However, we know that when theta is small, and this is why SHM can approximate the motion, not it doesn't actually undergo SHM, it's just approximated as an SHM equation, then we can replace sine theta with theta. In which case, this equation now becomes an SHM equation because you've got theta double dot plus g on L theta equals 0. And that is an equation for SHM because you've got a second derivative plus a constant times the function equals 0. Okay, so that is SHM. And in this case, omega will equal the square root of g on L. Which, interestingly enough, means that the period of motion does not depend at all on the mass. It only depends on what planet you're on. So if it's Earth, obviously it's going to be constant, and the length of the radius. Okay, really interesting fact there. Okay, so that's essentially the model. Let's just have a look at an example. Okay. So we've got a mass of 10 kilograms. It's attached to a light, inextensible string as shown in the diagram. We're going to derive a differential equation in theta and t, which governs the motion of the pendulum. We're then going to use small angle approximations to solve this differential equation. We're then going to solve it for a particular solution. And then we're going to find the amount of time it's below a certain point. Okay, fairly straightforward question. So let's start from the top. Okay, we're going to derive a differential equation for this. So just as before, we're going to draw out our little diagram. So to answer part A, there's my mass. This time it's got a mass of 10, so its weight is 10g. It's got some kind of tension force acting that way. And then that's going to be at an angle theta to that direction. And we're taking that to be positive because theta is increasing as you go up to the right. And then if I apply F equals ma in that positive direction, then I'll end up with minus 10g times sine of theta equals the mass, which is 10 times x double dot. X double dot, well, x is 0.2 theta because it's 20 centimeters. So therefore 0.2 meters, we should stick to SI units. So the distance it travels around the arc of the circle is equal to 0.2 times the angle subtended at the pivot. So we can differentiate that, so we get x double dot is equal to 0.2 theta double dot. Okay, take this and plug it into there, the 10s cancel, bring that across the other side, and that'll give us our governing equation of motion. And we end up with theta double dot, and then we need to divide this by 0.2, which is the same as timesing by 5, so that's plus 5g times sine of theta equals 0. That's the differential equation which governs the motion of our pendulum. Okay, part B. Using small angle approximations, solve this differential equation. Okay, so this is where we now are going to apply small angle theory to the problem. So for part B, for small theta, sine theta is roughly theta. So that changes the differential equation to be theta double dot plus 5g, which is 49, times theta equals 0. So from there, we can just solve that differential equation. So the auxiliary equation would be lambda squared plus 49 is 0. And that means that lambda must be plus or minus 7i. Okay, a pair of imaginary conjugates. Okay, so now that we've got those two solutions from our auxiliary equation, we can jump straight to our general solution, which is going to be theta is equal to some arbitrary constant times the sine of 7t plus some other arbitrary constant times the cosine of 7t. And of course you could have the sines and cosines the other way around. That is absolutely fine. Feels a little bit wrong because we've got the angle outside of the trig and we've got time inside the trig, but I can assure you this is the correct answer. Don't forget it is, though, an approximation to the motion. Okay. Part C of the question. The mass is lifted to a point such that the string is taut at an angle of 15 degrees to the vertical, and the mass is released from rest. Find the particular solution. So the first thing to notice is the question has given theta in degrees when we have to be in radians. So we're going to convert that 15 degrees to radians. And then we're going to plug in our values to get our constant values. So when t equals 0, then theta is 15 degrees, but 15 is pi over 12. Okay, to convert from degrees to radians, it tells us pi on 180. So that is pi over 12. And we're told it's released from rest, which means x double dot would be, x dot would be 0, which means x double dot would be 0. That also means then that theta double dot will be 0. Okay, so, theta dot will be 0. Okay. Okay. So t equals 0, theta equals 0. If I plug in t equals 0 here, that will disappear anyway because of the sine function. And I end up with b equals pi on 12. And then if I differentiate this with respect to t, I'll get theta dot. And then that's going to change to a cosine, that's going to change to a sine. So that's going to disappear when I plug in t as 0. And I'm going to end up with 7a equals 0, which means a equals 0. So those are my particular values for my arbitrary constant in this case, which means then my particular solution is theta is equal to pi on 12 times the cosine of 7t. Okay, and that was part C to the problem, wasn't it? Okay, so that's my particular solution to this problem. Okay, and finally part D. Find the total time in one period that the mass is more than 19.5 centimetres below the horizontal ceiling, and what percentage of the period is this? Okay, so this is 20 centimetres long, which means there will be time when it's more than 19.5 below the ceiling, which is horizontal. And based on the question wording, we can assume it starts above that point. So we just need to find the times when it equals 19.5. So I need a theta value for this. So if it's 19.5 vertically below the ceiling, and that length there is 20, then what is my value of theta at this time? Okay, so there's my diagram there. So theta, or the critical value of theta, so I'm going to call this maybe theta 0. That is going to be equal to arc cos, because I'm dealing with the adjacent and hypotenuse, of 19.5 over 20, which is 39/40ths. Making sure your calculator is in radian mode, we're going to do inverse cosine of 39/40ths. That's 0.2241. Of course, I'm going to write this in my answer, but if I need that number, I'm going to use this calculator answer. And also the negative as well, because by symmetry. So I also need to put in another theta 0 of minus 0.2241. So what I'm essentially looking for is on my cosine curve in one period of motion, which will look something like that. That's one period. I'm looking for the times when theta is less than this kind of critical value. So let's pop in that up there and one down here as well. It starts up there at pi on 12. This is 0.2241 and minus 0.2241. And essentially what I need to do is calculate when it is in between those. So for this motion here, this is when it is below 19.5 centimeters below the ceiling. And for this part of the motion here and here, this is when it is above 19.5 centimeters below the ceiling. So I need to calculate the green time, which is this time here, and then divide that by the total time to get the percentage. Okay, so it now just becomes a trig solving problem. So I need to find this t-value here, this t-value here. By symmetry, I can then just take that distance and double it, because that's going to be the same time difference between those 2 points. So I don't have to find all 4 values. So if I plug in theta is this value here into the calculator, then what I can do is I can do 1/7 times the inverse cosine of that number times 12 on pi. Okay, so I've essentially just plugged in 0.2241 in for theta, and I'm rearranged it to find the value of theta. That'll give me my first value here, which is 0.0776. Let's write that over to the side. So I'm going to put T1 and T2 there on my diagram so I can see what I'm referring to. And T1, according to the calculator, is 0.07764269495. And then to get T2, I'm going to do the same thing, except I want a negative in there. So if I just change this answer to a negative and run it again, then it gives me my updated version, my updated value, and I get 0.3711. So 0.3711562556. Okay, so the total time that it is below 19.5 is going to be 2 times the difference, so T2 minus T1, and it's twice the difference because there are 2 green sections on my diagram above. I'm looking for the total time in one period of motion, so that's there and back. So I'm going to do 2 times, and then I can just pop in A and S there for the first number, and then I'm just going to pop in some decimals for this one. 42692. Right, because I'm only going to write my answer to 3 sig fig, then I don't have to go all the way. So 0.587 is the total time. And because the length was measured in meters and G is in meters per second squared, then this is in seconds. Okay, SI units. But it also wants the total percentage, or that as a percentage of the total period. So the total period is that distance there. What time does it take to return to its starting position for the first time? That is defined as the period of the motion, and the period is 2 pi over omega. Omega is 7, so the total period is 2 pi over 7, which is 0.8. 897597901. Okay, so we want to find what this number is as a percentage of this number here. Okay, what is the percentage time that it is below 19.5 centimeters below the ceiling? So take this number here, divide by that number there, and we're good. Not times by 100. 587.027131 divided by the answer times 100 is 65.4%. So I'm going to write that as a calculation as 0.587 divided by 0.898, roughly that, and it comes out to be 65. I'm going to write 65% to the nearest percentage. Okay, 65.399, 65%. Okay, If you have any questions on anything I've said, please just drop a message in the comments below. And thank you very much for watching.